So welcome everyone to this second part of the afternoon session. So I'm Adolfo del Campo from the University of Luxembourg, and I will be chairing the first. We'll have two exciting talks for short talks. The first one by Marco Radaelli from Trinity College, and it's on precision mounts. So please go ahead.
Thank you. Hi everyone, good afternoon. I'm Marco Radaelli. I'm a PhD candidate in the Trinity Quantum Information Theory group in Dublin. And today I'm going to talk about precision bounds for multiple currents in open quantum systems. First of all, let me thank the organizers for the nice conference and for giving me the opportunity to present my results here. So we are going to talk about uncertainty relations in thermodynamics. In particular, the literature has identified two different uncertainty relations, the thermodynamic uncertainty relation and the kinetic uncertainty relation. They look the same. On the left-hand side, we have the variance of a time-integrated current along a process divided by the squared expectation value of such time-integrated current. What appears on the right-hand side is a little bit different, but the meaning is kind of similar. We have a trade-off between the precision of the currents, the relative precision of the currents, and how much entropy is produced along the trajectory, or how strong the signal should be, how strong the dynamical activity of the system should be. Now, in the following, we are going to mostly focus on the KURs because they give a little bit simpler formalism, but the results can be applied basically directly to TURs as well. So it has been known for a while at this point that quantum systems can violate classical TURs and KURs. In particular, we can consider a system like this. This is a three-level maser that has been presented a number of times during this conference. So we have three levels, 1, 2, 3 energy levels. The system is coupled to two baths, a hot bath and a cold bath. And there are jumps that correspond to the coupling between the system and the baths on both sides, and there is some kind of Hamiltonian driving between these two levels. As we at this point know very well, the dynamics of a system like this is described by a GKSL-like master equation. So it has been known for a while that this system can violate the TURs and the KURs. So if you look at the integrated currents of this system, they can be more precise, they can have lower fluctuations than what's allowed by the classical TURs and KURs. So the question here is, can we say something about what happens to quantum systems with respect to KURs and TURs? Can we come up with something that can replace KURs and TURs for quantum systems? So I'm going to present a method that has been introduced by Hasegawa and colleagues. I'm first going to present the method for a single parameter, and then I'm going to introduce our original contribution, which is related to the adoption of multiple parameters. So the trick here is to translate the problem of building TURs and KURs to a metrology problem. In particular, we add the dependence on a parameter, a fictitious parameter phi, in the Hamiltonian and in the jump operators of the dynamics. Of course, this basically corresponds to speeding up the dynamic of speeding up the dynamics or speeding down the dynamics. Of course, the original dynamics, the true dynamics of the system, is recovered for phi equal to 0. Now, what we observe for a system like this is something like this measurement record. I'm here using the same formalism that my supervisor Felix Binder used in his talk a week ago. And so here I use K to indicate the jump channel, the emission of the jump channel, the channel of an emission, and tau to indicate how much time has elapsed since the previous jump. Now, a counting observable, that is what plays the role of our time-integrated current, is a function of this kind of measurement record. And here comes the trick. Basically, this counting observable accumulates dependence on the parameter phi along the trajectory. This means that we can use phi as a big phi as an estimator for small phi. Sorry, the choice of the symbols is not the happiest. Okay, so in particular, we know from estimation theory that the precision of an estimation is bounded from below by the the error of the estimation is bounded from below by this kind of bound, which is a Kramer-Rao bound. We have seen this thing a lot of times during this conference, and this is true for unbiased estimators. So for estimators for which the expectation value of the estimator is the value of the parameter. Now, our phi in general is not unbiased. So we have to use a more general version of the Kramer-Rao bound, which is this. If you look at this, well, if the estimator is unbiased, this object is simply the expectation value of the estimator, which is phi. So the derivative is 1, and we return to the original version of the bound. Well, if we look at this, it's not very different from a kinetic uncertainty relation. Well, on both sides, we have the variance of the time-integrated current. It's a lower bound. Still, there are two things that remain to be done. The first one is that we need to somehow translate from this object to this object. And the second one is that we need to relate the Fisher information and the dynamical activity somehow. I'm going to discuss about the second part, so how to relate the Fisher information and the dynamical activity. The first problem, so relating this denominator to this denominator, is a lot more technical and cumbersome, so I refer you to the appendix of our paper for the details. Okay, so let us now consider the measurement record that is an object like this. So start with a jump, and then jump emission in channel K1, after time tau 1, and so on. The probability that is associated with this measurement record, which is the basic ingredient to compute our Fisher information, is given by this expression. In particular, this is what has been shown by Felix in his talk. So we have a trace of this giant object here, which is just initial state, coherent evolution, jump, and so on. In general, this is a very non-tractable object, because unless there are some kind of factorization properties, this probability distribution can be, this probability density can be extremely, can have extremely long-term correlations. This doesn't allow for any analytical manipulation usually. Now, we also have this kind of encoding, and this kind of encoding gives, every time there is a jump, gives a 1 plus phi factor that comes from here, and then something remains inside this term, and that's in particular due to the fact that the V contains the 1 plus phi factor in the Hamiltonian, and the square root of 1 plus phi in the jumps. So starting from here, we can ask what's the Fisher information contained in this probability distribution for our fixed issues parameter phi. And if you try to compute the Fisher information, what comes out is that, well, the first part here gives exactly the dynamical activity. So, and that's actually the significant trick. So this kind of encoding guarantees the fact that here we get exactly the dynamical activity, plus a correction, which is what's known as the Q parameter. And okay, this correction is what allows quantum systems to violate the classical bounds. So this correction in particular consists of the contribution of this complicated probability distribution, and it becomes 0 when we consider a completely non-coherent model. So if we use a model which has no coherences, we see that this second contribution becomes 0, and we come back to the original case. Now, of course, computing this object here is in general not feasible analytically, and we have to do it numerically. In particular, in this work, we use the monitoring operator formalism that was introduced by Felix in his talk as a way to basically compute this Fisher information. Then computing this object is quite easy. The dynamical activity can be computed on trajectories. And finally, one obtains the Q as their difference. So now we basically went from this to this. I've not talked, again, I didn't talk about how to go from here to here, but I mean, except for corrections that vanish in the limit for large times, it can be proven that these two things coincide. So this Q term is what allows the violation. In general, we cannot say anything regarding its sign, but if this Q is positive, then we can hope for violations of the classical limit. Okay, now, and so far I introduced the method which was discussed by Hasegawa and colleagues. And okay, now, what if we have multiple currents? So in this case, for instance, we can think about considering separately currents which deal with exchanges with the hot bath and currents that deal with exchanges with the cold bath. So for instance, we can ask, how can we bound a product like this? Well, in general, of course, these results are going to be valid. So something we can say is, well, okay, we bound each of them separately, and we get a bound that looks like this. So basically, in the right-hand side of this expression, each of the denominators is built by assuming that the other current has no encoding of the parameter, so it doesn't play a role in the TUR. However, if we plot the results, well, for now, ignore the red curve. So the black curve is here, which is the result obtained on trajectories of this thing, and the blue curve is here. So of course, the bound is satisfied, but it's extremely not tight. We are off by like 9 orders of magnitude. So what's the problem here? Well, the problem is that we are not yet considering correlations between the different currents. These currents do not happen in isolation, they happen together. And so can we do something to address these correlations and maybe hope that this allows us to get a better bound? It turns out that yes. What we do is that we encode multiple parameters in our fictitious encoding. So in particular, we assign a parameter phi1 to a fictitious parameter phi1 to every exchange that involves the hot bath, and the fictitious parameter phi2 to every exchange that involves the cold bath. So in particular, all the jumps involving the hot bath will have phi1, all the jumps involving the cold bath will have phi2, and the Hamiltonian will have both. Of course, again, the original dynamics is retrieved for phi1 equal phi2 equal to 0. Now, we use the formalism of multi-parameter estimation. This is the equivalent of the Kramer-Rao bound in the non-unbiased case for multi-parameters. I'm not going to introduce the details, but the idea is always the same. So we have the Kramer-Rao bound. This time, everything is a matrix. So the Fisher information becomes a matrix. We use the instruments of multi-parameter estimation theory, and we obtain new bounds. In particular, note that the Kramer-Rao bound is a matrix bound at this point. This means that this matrix minus this matrix, this matrix minus this matrix is positive semi-definite. We have to go from, we want a scalar bound. There are many ways of going from a matrix bound to a scalar bound. One of them is using the determinant, and that's exactly what we do. And what you obtain is this bound here. I didn't put the entire formulation of the bound because it's very cumbersome and not particularly insightful. You can find it in the paper. So what we find is an actual saturation of the bound from our calculation on trajectories. And so we can actually get a much tighter bound when the correlations are actually taken into account. So this leads me to my conclusions. So quantum systems, as we saw, can violate classical KURs and TURs. This has been known for a while. Hasegawa and colleagues discovered that quantum KURs and TURs can be obtained via the Kramer-Rao bound for a fictitiously encoded parameter where the fictitious encoding is crafted in such a way to retrieve the KURs and TURs. And finally, if we keep the correlations among the currents into account, this allows for tighter bounds in situations where we have multiple currents. With this, I would like to thank you for the attention and thanks my collaborators, Saulo Moreira, Alessandro Candeloro, Felix Binder, and Mark Mitchison on this paper. Thank you.
We have time for questions.
Hello, thanks for the nice talk. So I was wondering if you're aware of recent results pointing to thermokinetic uncertainty relations so that they kind of combine to the dynamical activity and the entropy production to get some tighter bounds. So I was wondering if you can also do this kind of multi-parameters there. And
I guess if it can be done, I didn't read the specific result, but if it can be phrased in terms of the Kramer-Rao bound for a single parameter, then I guess the multi-parameter should be feasible in principle. Yeah. But I'm not aware if anyone has ever done that for
in any case, I guess for the TOR, you need to use a different kind of deformation of the, of the dynamics.
Exactly. In particular, I mean, the reason why I presented the KURs and not the TORs is that for the KURs, you need a deformation that depends on the state, which in general makes the dynamics nonlinear, which is not a problem because then we use the phi that goes to zero limit. So in any case, the real dynamics is still linear, but it was harder to present. But yes, definitely.
Thank you.
More questions?
Hi, thanks for the talk. Did I understand well that these bounds depend on the kind of detection you're assuming you're doing on the output? So this feature information depends on the unraveling.
Sure.
So you can actually optimize over that. So you have this, so this bound can be optimized over all the possible unravelings somehow?
I would say so, but I would also say that the object on the left depends on the unraveling.
True, okay.
Because here we have a current that depends on the measurement rate.
Sure.
Yeah.
Okay, so that's, okay. But you have maybe more violation, okay.
Could be, yeah.
Okay.
One more question here.
Hi, thanks for the talk. So just to be clear, these are all statements about steady state dynamics, right? Or it's valid also beyond that, like in driven regimes?
I'm not sure if I get the question, honestly. Can you expand a bit?
So, for example, TURs can be violated if you drive the system.
Yeah.
I'm not very familiar with KURs, so that's why I'm asking the question.
Okay.
Are KURs valid or stop being valid if you start driving the system, or?
Okay.
So if you have any type of dynamics involved, or it's in the sense that like non-steady state.
I don't know. It's a good question, but I don't have a good answer. Sorry.
Maybe I can make a comment as well. So I think TURs have been related to quantum speed limits. So they're related to Cramer-Rawan. So they are a bit like the Mandelstam time energy uncertainty relation. Are there bounds in the spirit of Margulis-Levitin?
Sorry, is there bounds?
Are there extensions of these TURs which are related to the first moment, of the generator? Like the Margulis-Levitin bound, or to other moments?
Not that I'm aware of, at least.
Okay.
Yeah.
Thanks. All right, so let's thank the speaker again.
Thank you.